Hello, friends. Let us now learn some important points about the ultrasound. So, one important thing is for X-rays, X-rays were used immediately after their discovery, but ultrasound took a lot of time for it to come into its diagnostic use. So, ultrasounds were discovered many years back. The first use of ultrasound was in 1912 for the discovery of Titanic. Later, in World War II, that is in almost 1939s and 1940s, the in World War II, there is something called as sonar. Sonar is sound navigation and ranging. This sonar, which is sound navigation and ranging, is a successful application. And later in 1940, only after the war, and in 1950s, the ultrasound has been utilized as a medical imaging diagnostic. So, if you see an ultrasound, ultrasound will contain sound waves, right? A sound beam which is almost similar to the X-ray beam because this sound also has, just like X-rays, it has a wave, and it is a wave and it is transmitting energy. The important difference between X-rays and the ultrasound is that X-rays will travel through vacuum also, whereas sound does not travel in vacuum and sound requires a medium for it to travel. So, the best way to depict the propagation of sound is that if the particles are connected are separated by tiny springs, if atoms or molecules are separated by tiny springs. So, when you give a force, the first particle will be pushed, it moves and it compresses the attached spring. This attached spring, this will set up a chain reaction. Okay, when you compress a molecule, that will compress the next molecule, that will compress this chain, and this will compress the other molecule. This other molecule will again compress this string and it will compress the other molecule. So the tension or the pressure applied to the spring is greatest between the first two particles. The tension or pressure applied by the spring is greatest in the first two particles, and as the pressure propagates, the pressure will decrease. So this is like a spring. Spring will have elasticity. So this will, if the driving force will reverses its direction, the particles also reverses its direction, and they will come back to their original position. So sound is like that. The force, when force vibrates to and fro, like an oscillating pendulum. So if you hit a pendulum, it goes to and then fro, it goes to and then fro, right? So similarly, these particles will also vibrate to and fro, and they will oscillate, and the sound propagates through the medium. See, when the sound is struck here, when the force is exerted here, the first particle will move a distance of a, whereas the sound, or actually the effect which is sound, is propagated through a distance of b. So this is one important characteristic. Second, how is sound wave generated? So sound wave is a longitudinal wave. Sound waves are transmitted in liquids as a longitudinal wave. So what does this longitudinal wave mean? Longitudinal wave means this longitudinal wave means the motion of the particles in the medium. So this is the medium. The particles are moving like this, and they are parallel to the direction of wave propagation. The wave is moving like this, and also the motion is also in the same way. The motion of the particles in the medium is parallel to the direction of wave propagation, that is called as sound wave. In sound wave, whenever a force is applied here, these molecules are compressed. Okay. In the second time, this is for first second. In the second, this compression transmits to this place, and again in the third second, again a force is applied, and as a result, the sound wave is actually, each cycle there is new wave production, and the length of the wave is the distance between the two bands of compression or two bands of rarefaction. So this is compression, whereas this is rarefaction. So the distance between two bands of compression and rarefaction is the length of the sound wave. So the same thing can also be plotted on a sinusoidal curve also. So if you plot it on a sinusoidal curve, it will be something like this. There will be propagation of sound will occur. So if you see ultrasound has a frequency of 20,000 cycles per second, whereas the audible sound which we are going to hear, this has a frequency of around 15 to 20,000 cycles per second, whereas the sonic sounds which are used in diagnostic imaging, sonic sounds which are used in diagnostic imaging will have almost 1 million to 20 million, 1 million to 20 million cycles per second. Okay. If you see, one cycle per second is called as 1 hertz. 1 million cycles per second is called as 1 megahertz. Okay. The next important thing. The next important thing is velocity of sounds. Velocity of sound is actually independent of frequency. And for the sound, independent of frequency, and velocity of sound is mainly dependent on the material or the medium in which the sound travels. And medium has two properties. Medium can be compressible and at the same time density. So the velocity of the sound depends upon the compressibility and density of the medium in which it travels. So if you see here, the highest, those which transmit rapidly are solids. All these are actually solids which will transmit sound fast. Then intermediate sound transmission is present in liquids, and least sound transmission is present in airs. All body tissues, fat, kidney, blood, muscle, all these will act as liquids only, except bone, which will act as solid. Then let us learn some important points about the compressibility. So if you see the velocity of sound, velocity of sound is inversely proportional to the compressibility of conducting material. The more compressible the material is, the lesser will be the sound. The less compressible the material is, the more rapidly it transmits. So gases are more compressible, so as a result, they have less velocity. Whereas solids are less compressible, so they have more velocity. The explanation is that if solids are less compressible, they are closer to each other, so they can distort the neighbors very easily. So as a result, they can affect the neighbors easily so that the sound can propagate. Then the velocity of sound also depends upon the density. The denser the materials means they contain more massive molecules. So because they contain more massive molecules, they have increased inertia. So if they are denser, the molecules, if you see the density, I'll give you two examples from this chart itself. Mercury is more dense when compared to water. So mercury has increased inertia. Okay, because mercury has increased inertia, propagation of sound mainly includes rhythmic starting and stopping of particulate motion. So, if there is more inertia, it will take more time for it to start and more time for it to stop. So, as a result, mercury will take less time to will actually mercury should take less because of more density, more inertia. Mercury should have less velocity when compared to water, which has more velocity. But in reality, if you see the values, the velocity of mercury is almost equal to that of velocity of water. Why? The main reason is explained by compressibility, because the water is more compressible when compared to mercury. So mercury is more denser, but water, because it's more compressible than mercury, the compressibility of water is almost 13.4 times as compressible as mercury. So as a result, because of its more compressibility of water, velocity will be less. Less compressibility of mercury, velocity will be more. Both this velocity and compressibility are both this density and compressibility are cancelling with each other. So as a result, the velocity of water and mercury are almost similar to each other. Okay. So if you see the relationship between wavelength and velocity, velocity of sound is equal to frequency nu into wavelength. So velocity is equal to frequency nu into wavelength. In ultrasonic frequency range, In ultrasonic frequency range, velocity is constant in any particular medium. So if you see the velocity of this, if you see in the figure 20.3, which is shown here, this vibrator, we have vibrator which is vibrating at two different frequencies. Vibrator A will have a frequency of 1.5 megahertz. And think that the medium here is water. So this water will propagate sound at a velocity of 1540 meters per second. So if you wanted to calculate the wavelength, so velocity is equal to frequency into wavelength. So 1.5 into 1 million hertz is equal to uh, sorry 1.5 into 1 million hertz is the frequency, which is nu, okay, into wavelength is equal to velocity 1540. So wavelength we get has 1540 by this 1.5, that means almost into 1 million. So you will get almost 0.001 meters. Therefore, the wave can propagate through 0.001 meter, that is equal to 1 millimeter, in the available time before a new wave starts. Before a new wave starts, that is the wavelength will be almost 1 millimeter. Before a wavelength starts, the wave propagates for 1 millimeter. Similarly, if you do the same for a third 3 megahertz, then obviously the wavelength will decrease, right? Because it's almost double. So it's sorry, frequency is doubled. So wavelength it becomes half. Okay. Then the next property of the sound is about the intensity of sound. Okay. So this is the intensity of sound. What is intensity of sound? Intensity of sound, also called as loudness of sound. Intensity of sound or loudness of the sound is length of oscillations of particles conducting the waves. So this figure will show intensity of sounds and its relationship with bells. So let us see. Okay, one. Now, if we see the intensity, if you see it's 1.5 hertz, this is 3 hertz. Okay, you see this is 1.5 hertz, and if I'm going to see 1.5 megahertz, bands only, and I'm going to draw those with higher intensity. This, imagine it's low intensity. Now, if I draw with high intensity, there will be more denser contractions will be there, and rarefractions will be more loose. Again, you will have denser contractions. The compressions will be denser, whereas rarefractions will be lighter. Compressions will be even more denser. The rarefractions will be lighter. So that is the difference between the high amplitude and low amplitude. So because the vibrator here will stuck harder, so more energy it receives. So more energy it receives, so there is more vibrations. Then there is more, these ray fractions will be more wider, and again there will be more energy it transmits. So there is more vibrations. So ultrasound intensities here whenever there is high intensities will produce more vibrations and more ray fractions, whereas the more compressions and more rare fractions. So whereas the wavelength will be same. So the vibrations, as the time increases, as you see, if the time increases, the vibrations will diminish in intensity also. Ultrasonic intensities are mainly expressed in watts. So one more important thing that you should see is that, which I did not highlight in this picture, is that as the time increases, these intensities will also decrease. There will be high intensity than this, but the intensities will decrease as time increases. Okay. The ultrasonic intensities are measured by watts per square meter. Watts per meter square. The ultrasonic intensities are measured by watts per meter square. The next important thing is the relative sound intensity. So, as you see, intensity is measured by watts per meter square. But see, all these values are really very difficult to understand. So, for that, we have started using relative sound intensity. Relative sound intensity is measured in decibels. Decibel is 1/10 of the bell is called as decibels. So, decibel is actually a logarithmic power. It is a relative power of two sound beams expressed logarithmically using a base of 10. So here the relative intensity of sound is the decibel, and this relative intensity can be given by the formula log base 10 of intensity of sound 1 by intensity of sound 2. This is called as decibel. So bell, we can define bell as logarithmic expression of relative intensity of two sound beams. So for example, if original sound has intensity of 10 watts per centimeter square, whereas the returning echo I2 has 0.001 watt per centimeter square, centimeter square, then I2 by I1 is equal to 0.0001 by 10, that is equal to 0.0001, that is equal to log base 10 is 10 to the power of minus 4. So 4 is the, this called as minus 4 bells or minus 40 decibels. Decibels can have a positive sign or negative sign. Positive sign will mean that there is increased power. If there is negative sign, it means that there is decrease in power. It is actually based on the increase or decrease in power. So this is about the intensity of sound. So these are the important properties of sound. Thank you.